Thank you. Good afternoon. My name is Fang Huang from Louisiana State University Agricultural Center. I'm a field crop pest management entomologist. The title of my presentation is Lessons and Perspectives from 3 decades of global IRM for BT crops. In my presentation, first I'm going to have a brief introduction about BT and BT crops. Then I will talk about what have we done in BT crop IRM. IRM means insecticide resistant management. And I will share some successful and failure stories in BT crop IRM. And now we'll talk about based on those stories, what we have learned. At the end of my presentation, I will list a few future work we think we need to be emphasized. BT actually is a very common soil bacteria. They can produce many different BT proteins that toxic to insect pest. BT actually, as a microbial insecticide, has been used since the 1930s. That's about 100 years ago. BT microbial insecticide are famous for environmentally safe, and they also have a low impact on non-target organisms, including higher animals and human beings. BT is the most commonly used microbial insecticide today. Most of the organic farmers actually relied on BT to control their insect pest. Because of the very excellent property of BT the insecticide toxin, and then scientists has transferred some of those BT gene into crop plant. So those plant can produce BT proteins by themselves, and then when insect eat those plant, they kill the insect pest directly. Among the BT crop has been transferred. The BT cotton, BT corn, and BT soybean are among the most widely planted BT crop today. Okay, and now other several BT crop also commercially planted in the world, but the acreage are much smaller. BT are very effective usually to the insect species they targeted. Okay, they are also excellent in yield prediction because of the high efficacy and easy use. The adoption of BT crop has been rapidly increased since the first year they commercialized in 1996. Today, we plant about more than 100 million acres of million hectares of BT crops in the world in about 25, 26 countries. And then the American countries like Brazil, USA, Argentina, those count for about 80% of the total planted acreage in the world. However, the insects can develop resistance to those BT crop. Actually, even before we commercialize those BT crop with low insects will developing resistance to the crop, so that we actually require the farmers will require the IR system we required to have a resistant management program to be adopted in the US and several other countries to plant the BT crops. Okay, and in the next few slides, I just want to show what we have done in BT crop IRM. We actually implemented 3 strategies: the refugee strategy, another one called the high dose plus refugee strategy, another one called the gene permitting strategies. And then besides those 3 strategies, we also are required to monitor the resistant development in the field. For the refugee strategy means we're planting non-BT plants or use the natural host plant to serve as refugee for the susceptible population so that the susceptible population can mate with the resistant population from the BT crops. And then that can dilute the resistant allele frequency in field population. For the high dose refuge strategy means we planting the beet crop, they are qualified as high dose, means they can kill the heterozygous individuals by more than 95%. And then at the same time also provide refuge for the susceptible population, and then so that this large susceptible population from the refuge area should mate with the real homozygous resistant that survived from beet plant. And in this way, the most of the offsprings not carry resistant allele should be heterozygous individuals. Those heterozygous resistant individuals should be killed by high dose beet plant so that the resistant allele frequency in the field population should be maintained at a low level for long period of time. There's another strategy called gene pyramiding. That's we plant the BT plant express two or more BT genes that kill same species. Like they both got the two cotton. They contain Q1AC and Q1B two protein. Both kill the bollworm or tobacco bottle worms. So we implemented those strategies, and then we like to see what the result. But as you know, those kind of strategy we cannot directly use a field trial to show to document if those strategy are working or not. However, we can get some information from the 20, 30 years plant of the BT crop in the field. We get those information from the from the history so that we can learning if this we can judge this the strategy as success or not. So before I talk about those success or failure stories, I want to introduce two terms. One is called a case of resistant, means a resistant of one pest species in one country to one BT protein in one crop. Okay, and then another term called field resistant means there is a control problem due to resistant development in the field. So a case of successful IRM means the field resistant has not occurred. Or a case of IRM failure means the field resistance has already occurred. Okay, there are four successful stories for the IRM. For the those four stories are the four major pests of the corn and cotton remain susceptible after 30 years of intensive use of BT corn, Q1AB corn, and Q1S cotton in the U.S. Those four insect species are the European corn borer and Southwest corn borer for BT corns. And the tobacco butterworm and pink bollworm, those are two major target of BT cotton or Q1SA cotton. Today, those populations they're very susceptible to the Q1AB protein or Q1SA protein, and then we categorize their successful stories. We also have documented more than 30, like 32 cases of confirmed field resistance to BT crops. Those are less of those 32 cases. I will not read each one for details. In summary, if we summarize those 32 cases, what we can say from this figure by years. Those years of the cases it's based on the confirmation be published in reference journal. So as you can see, the first 15 years we just have two documented case be published, and then many 30 are after 15 years. Actually the resistance occurred actually several years before the information be published. So based on those successful story and failure story, what we have learned. First, we learned about the failed resistance. Those unsuccessful story are highly related to the use of non-high dose trade. For example, the four cases with successful, all of the four cases are actually qualified as high dose. We documented this story actually 15 years ago. After 15 years, those are stories still standing. And then we also get some published information to show all of the six field cases with field resistance, they are not high dose. Here is the dominant level significantly bigger than than point and than zero means the plant did not produce high dose. Okay. And now if I do a little bit of summary, you can see for the case with field resistance, the average dominant level is 0.63. And now for the cases they have recently have not occurred, the dominant level is only 0.11. And then the second biggest lesson we learned is the improper use of pyramiding strategies. What is, I call it the most sequential use of BT protein in pyramiding. What this means, I can just use the BT corn as a story. At the very beginning, in 1996, we just planted a single gene Q1AB corn, or some we also have some Q1SA corn. And then after 7 years, we planted Q1F corn. Okay, Q1F corn, single genes. And then after several years, we planted so-called pyramided BT corn. They have two different types. One is Q1A 105 plus Q2AB2. One is Q1F plus Q1AB. Actually, the Q1A115 is a combined toxin and like Q1AB, Q1SA, and Q1F. So there are a lot of new. The only the Q1AB is Q2AB is a new gene in the pyrimidine trade. And then for the second group, Q1F plus Q1AB, they actually all are older protein. And then after several years, we added one more new protein, YP3A, into those older protein, and then we call them pyrimidine, even call the second generation pyrimidine. So what is the problem for those sequential planting of BT pyrimidine corn or plant? So there only a single new gene was added in each introduction of new pyrimidine trait. Okay, other genes has been used for many years. They either some of those genes either already lost activity or the recent new frequency for the gene has been very high. Okay, so plus both of the cross resistance among quite one gene, quite one protein also, or from among quite two proteins. All of those could reduce the effectiveness of the pyrimidine greatly. Another lessons we understand is the mode of action are very limited in the transgenic BT plants. Although we have 100 different BT plant trait or many different genes, what I can show here, we can actually do a little bit of work to categorize those BT genes in the BT plant into only three categories or three groups. The quite one group different based on the different mode of action, and quite two group or VIP3A group. And then those quite one genes in the quite one group, they are cross-resistant similar mode of action, similarly for the quite two group and the VIP groups. And another problem we found is actually the growers did not adapt the required planting of refugee size, not very good. Okay, for example, the U.S. EPA survey here showed like 2017, only 19% of the growers beat the refugee size planting. However, we actually there is lots of other lessons we learned, but I just show those major one we I believe. Okay, and then there are another good thing also we learned the field resistance is reversible. Okay, one story we documented the F resistance in the for armyworm in the coast area, east coast area like Florida, South Carolina, North Carolina, in 2011, 2013. But after a decade later, we made another surveys, but we found the population even in the entire south region of the United States become susceptible to the Quran F protein, include those population actually connected from the area we documented the field resistance 10 years ago. So this actually the first documented cases of reverse the field resistance could be reversed to susceptible. And there's here I listed some of the future work things needed to be emphasized. First, we need to discover more mode of action, include the use of non-BT insecticidal transgenes like RNAi or gene editing. Okay, and we also need to use different mode of action for different crops. We also needed to like avoid the use of pyramiding trade sequentially. This is the industry has a grade to produce future kind of planting, at least including two new protein at the same time. Okay. Another thing, we needed to improve the monitoring for earlier detection of resistant development. Currently, resistant monitor program by the US EPA, actually, they just monitor like a field resistance or called practical resistance. They cannot monitor the earlier stage of the resistant development. We also like to incorporating the IRM program into the IPM program to diversify the mortality factors that try to reduce selection pressures. And another very important work we needed to do, I think, is in the past, most of the research focused on like the high dose refugee strategies, and then future research were like needed to be done for the like for the IRM program for non-high dose trade should be evaluated and deployed. We also needed to understand the like dual or multiple gene resistant, and then in the past we usually focus only the single gene resistant. Okay, of course, at the end, we like to develop in a landscape IRM program and to try to reduce the cross-cropping resistant problems. And nevertheless, I believe the conservation of BT susceptibility will continue to be a great challenge in the future. That's all I'd like to show today. Thank you very much.